Hi, my name is David Bischel, and I was granted the opportunity by University of Michigan's Optics in the City of Light, iREU, to work under Professor Laurent Daniel analyzing X-ray diffraction images of piezoelectric ceramics. Deriving its name from pressure of electricity, the piezoelectric effect involves the deformation of a material to produce a net voltage, or the application of external voltage to induce a deformation. The experiments performed deal with this latter instance. X-ray diffraction is employed to shed light on the minuscule scale of the local piezoelectric effect. Bragg's law tells us that a crystal plane will diffract an incident beam if it forms a precise angle theta with the beam. In a bulk material, there are many of such planes, and the diffractions culminate in a series of concentric circles on the measurement plane. If the crystals are somehow preferentially oriented, say due to some external electric field or applied stress, then this once neat circle will be ruptured by variations in intensity. Because of this dependence on the angle psi, the diffraction image is sliced into cakes at different angles and summed across each cake to give a linear profile that is then ready for analysis. If there is some strain in the material, this manifests as a change in the lattice spacing of the constituent crystals. The peak locations in theta then change according to Bragg's law with changing spacing d. If the lattice set has non-uniform dimensions, the different orientations of the crystal within the material will cause it to form a double peak on the linear profile. To determine the local strain from this set, we must know the relative presence of both orientations. An external electric field can cause a crystal to reorient from one grain direction to another, and one peak then grows at the expense of another. This volume fraction is often calculated as MRD, multiples of random distribution, which is then used to calculate the average lattice spacing and strain of the lattice set. Preliminary analysis has also been performed on a set of data in the longitudinal mode, where the electric field is applied parallel to the stress. In these experiments, samples of lead zirconium titanate, or PZT, of different compositions are subjected to a varying electric field, known as a Rayleigh loop. With the help of MATLAB, we have observed that orientations cardinal to the electric field accumulate a residual strain, while the orientations ordinal to the field do not. But further analysis must still be done to verify this. For the latter reversible cases, the piezoelectric coefficient can additionally be calculated from the tilt of the hysteresis loop of strain versus electric field. I would like to thank University of Michigan for offering this opportunity, the National Science Foundation for sponsoring it, and Professor Laurent Daniel for allowing and aiding me to contribute to his research. Thank you for your time and your attention.